Swayam Prabha. Digital India. Educated India.
I welcome you all to lecture number 25 on the topic conduction mode of heat transfer. Before seeing the contents of this lecture, let's have a quick recap of what we have discussed in the previous lecture. Actually, by the completion of lecture number 24, we have completed the module number 4. So, module number 4 started from lecture number 17 and up to the previous lecture, that is lecture number 24. If we recollect the contents that we have discussed in the module number 4, primarily it was focused on the refrigeration and the air conditioning systems. So, we started the module number 4 with the principles of psychrometry. Psychrometry is the branch of science which deals with the study of air water vapor mixtures. What are all the terminologies involved: dry bulb temperature, wet bulb temperature, dew point temperature, specific humidity, relative humidity, enthalpy, etc. And we have studied about 8 to 9 psychrometric processes: sensible heating, sensible cooling, humidification, dehumidification, then the combination of sensible heating and humidification, combination of cooling and dehumidification, evaporative cooling, chemical dehumidification and mixing process. And these psychrometric processes are essential, and also the study of science of psychrometry is essential because as air passes from one heat exchanger to another heat exchanger, from one process to another process, it undergoes lot of thermodynamic changes. Then we have seen the working principle of a vapor compression cycle. We have compared the ideal cycle with the actual cycle, how the actual cycle deviates from the ideal cycle. We have discussed about the methods of improving the COP of the ideal vapor compression cycle. COP is the ratio of refrigerating effect or the amount of cooling produced in the evaporator to the work of compression, that is power drawn by the compressor motor. So, if you want to improve the COP, either we have to increase the refrigerating effect, enhance the refrigerating effect, or decrease the power consumption. Subsequently, we have discussed about 3 methods of COP enhancement. One is subcooling, that is subcooling the liquid refrigerant below saturation. Then superheating the that is by the time the refrigerant enters the compressor from the evaporator, it is slightly superheated. Then a combination of superheating and subcooling. So, we have made a comparison of the COP among these improvement methods. We compared with the base cycle without subcooling and without superheating. Then we have seen the absorption system, which is a heat operated system which does not use a compressor. Instead of compressor, it uses a set of heat exchanger, namely absorber, generator and solution heat exchanger, apart from other components like solution pump and pressure reducing valve. So, there is a concept called solution, which is a combination of refrigerant and absorbent. We have discussed the construction and working principle of water lithium bromide system, in which water is the refrigerant and lithium bromide is the absorbent. And in case of ammonia water system, ammonia is the refrigerant and water is the absorbent. And we have also discussed about the thermodynamic properties which are required for the selection of refrigerant, absorbent and solution. So, we have also discussed in detail about the desirable properties of refrigerant. What are all the types of refrigerant, primary and secondary, and the refrigerants are further classified into pure fluids, mixtures. In the mixtures, we have seen azeotropic mixture, zeotropic mixture. Then in natural refrigerants, inorganic refrigerants, all these types of refrigerants we have discussed, and also how to designate a refrigerant, what are all the various parameters based on which the refrigerant is selected, thermophysical properties, chemical properties, environmental properties, which is very important. If we take the environmental properties, we have discussed about the refrigerant should have a 0 ODP, ozone depleting potential. The global warming potential should be as small as possible. It should not be high or even at the moderate level. And there is another environmental property, that is the total equivalent warming impact, which is the summation of direct emission and indirect emission. So, it gives the total CO2 emission per kilowatt of hour of the electrical energy. Then we have discussed about the different types of air conditioning system, that is in the previous lecture, like split AC, window AC. These systems are called unitary systems. Unitary systems means, especially the split AC is called the unitary system in the sense the components are housed in a single box or in a single enclosure, and split AC slight difference from the window AC in the sense that the high pressure devices, the compressor and the condenser are placed in the outdoor unit, whereas the evaporator and the expansion device placed in the indoor unit. Then we have the cassette type of air conditioning system. So, apart from this, we have discussed about the chilled water system, variable refrigerant flow, which is also called as variable refrigerant volume system. This technology was invented by the Japanese company Daikin. And we have seen how the selection of air conditioning system for which applications. This air conditioning finds its application in commercial, industrial, residential. It is used in almost every places. Now, let us see the contents of this lecture number 25. This is primarily actually from lecture number 25 till the 30th lecture. So, we will be studying about some basics related to heat transfer mechanisms, conduction, convection, radiation, then design of heat exchangers. Actually, this heat transfer itself is a core subject. It is a full subject. So, for in this course, few topics related to heat transfer, like the modes of heat transfer, conduction, convection, radiation, and the composite wall, how to analyze a composite wall, which is a multi-layered wall, and how to design a heat exchanger. There are a couple of methods which are available. So, in this lecture, we will be focusing on conduction mode of heat transfer. So, the contents of my presentation are introduction, heat transfer mechanisms, heat conduction in a plane wall, cylinder and sphere. Then we will see about compare the thermal conductivity property of a few substances, and based on the discussions and the theory, the principles which we are studying, we will be solving some numericals. So, how this heat transfer differs from thermodynamics? So, that is very important one. So, one should know the difference between the thermodynamics and the heat transfer. If you look at the subject thermodynamics and thermal engineering, which it is if you see the contents, for all the 5 modules, a few modules are related to thermodynamics, few modules are related to thermal engineering, which is nothing but the application of thermodynamics, and this module 5 is pertaining to heat transfer. So, it is a branch of science which deals with the rate of energy transfer. So far we have heard or discussed about this term like conversion of heat into work, which is what we discussed in the Kelvin-Planck statement of the second law of thermodynamics. For any engine operating between a source and a sink, the heat supplied is converted into some amount of heat supplied is converted into useful work, while the remaining amount of heat is rejected. And we have clearly discussed this in the Kelvin-Planck statement, which clearly says that no engine can operate by exchanging heat with a single thermal energy reservoir. And similarly, we have discussed about heat pump and the refrigerator pertaining to class A statement of second law of thermodynamics. So, now this heat transfer, it's primarily focused on the rate at which the energy is transferred. So, this is very important, the rate at which energy is transferred. For example, let us have a hot fluid. Okay, let us take the fluid. When I say fluid, it could be liquid or gas. So, the hot substance is at 75 degrees centigrade. The outside condition, the ambient temperature is say 35 degrees centigrade. So, there is a delta T of 40 degrees centigrade. So, obviously, there will be heat transfer. We know that for heat transfer to take place, there should be delta T. If there is no temperature difference, then there is no heat transfer. So, the heat will flow from the hot fluid to the cold fluid. Suppose after some time, if you see the temperature of this hot fluid would have reduced to say below 75, 60 or maybe 55. At one stage, this process will continue until thermal equilibrium condition is established. So that means there is no change in the temperature between the system and the surrounding. So if you compare the thermodynamics with heat transfer, so I have mentioned, in thermodynamics we study the amount of energy transferred, how much heat is converted into useful work or vice versa. In heat transfer we study the rate at which the energy is transferred, how much time in how much. Suppose if a solid object is cooled in a cold environment, so how much time it will take for the temperature to be in line with the cold environment, like for the system to attain thermal equilibrium. So in this case, the reduction in temperature will not take place as it is, like in the sense it will take gradually. From 75 it will not come to 35, which is the surrounding temperature, in a fraction of a second. So the process will take place in a gradual manner. So as far as the mechanisms of heat transfer is concerned, conduction, convection and radiation. Okay, so this lecture and the next lecture will be focused on conduction, and one lecture on pertaining to convection, one lecture pertaining to radiation, and the remaining 2 lectures will be on heat exchangers. So it is a mode of heat transfer which takes place due to the vibration of the molecules, that is due to the vibration of the molecules. So this can take place single body from one region to another region, or between two bodies, So it can take place in all the 3 phases: solids, liquids and gases. So the energy transfer in liquids and gases, especially it is due to the collision and diffusion of molecules, the liquid and the gaseous molecules. So this requires a medium. For the conduction to take place, a medium is required, and not like radiation. The governing law for conduction is Fourier law of heat conduction. So we will be seeing what is this Fourier's law of heat conduction. So this is a plane wall. I have shown the schematic shown the plane wall where heat transfer takes place in this direction. I have given the direction. So T1 is the temperature. T1 refers to the higher temperature and T2 refers to the lower temperature region. Okay. So heat will flow from high temperature to low temperature, that is quite obvious. The thickness of the wall, this is not length of the wall, this is the thickness of the wall. The thickness of the wall, it is taken as a dx. Okay, so I have taken a small, which is equal to L. So in heat transfer, both theory and numerical questions, whenever we say for a plane wall it is dx, it refers to the thickness which is equal to L. We do not use the symbol, or in some books might be using del, small letter del, but otherwise we can use dx or capital L. So here, what does this Fourier law of heat conduction says that Q is directly proportional to the amount of heat flowing, it is Q. Temperature difference is delta T, that is T1 minus T2. Okay. And the thickness of the wall is, as I mentioned, it is dx, which is equal to L. So the rate of heat flow is directly proportional to the area of the plane wall and the temperature gradient. Temperature gradient is change in temperature with respect to the location. So here, as at this point the thickness of the wall is 0, and at the right extreme the thickness of the wall is L, that is dx. So at the midpoint it will be L by 2, half the thickness of the plane wall. Okay. So this Q is directly proportional to the temperature gradient. Temperature gradient is change in temperature with respect to the thickness. So, dt by dx, dt by dx. So, in order to remove the proportionality symbol, so a constant is introduced. That constant is called K, which is nothing but the thermal conductivity of the wall material, which is in watt per meter Kelvin or watt per meter degree centigrade. Okay. So, that is K. So, the parameter which is introduced to remove this the constant which is introduced to remove to replace the proportionality symbol is thermal conductivity of the wall material, the material that is used to construct this plane wall. So, it may be the K value may vary, it may be small, very small, or it may be a medium value, that does not matter. So, that is the whatever the construction material which is used for this one. So, that material has got some K value. Now, we can write dt by dx is, so generally when we write delta T, final temperature minus initial temperature. Here, for suppose if we take the initial state is 1, final state is 2. So, heat is flowing from 1 to 2. So, that is from temperature T1 to T2. So, when I write delta T, it is T2 minus T1, T2 minus T1. But if you see, if you calculate T2 minus T1, it will be negative value. Suppose if you take T1 as 35 degree centigrade, T2 is 30 degree centigrade. So, 35 to 30, the difference, if we calculate the difference from T2 to T2 and T1, it will be negatively, whatever may be the number which we take for calculations, because T2 is less than T1. So, the difference will be negative. So, now I am writing here T2 minus T1, K into A into, instead of dt I have written T2 minus T1 by dx. So, there is one negative sign which is introduced here. So, this is the negative sign indicates the heat transfer in the positive x direction. So, heat transfer in the positive, that is in this direction, in this direction. Okay. Here x is equal to 0, the thickness of the wall is 0, here x is equal to L. So, the moment I introduce this negative sign, so T2 minus T1, I will, this one, that will be negative value. So, minus of minus will become plus. So, Q equal to Ka into T1 minus T2 divided by L. That means, if I know the thermal conductivity of the wall material, delta T of course we know, and the area of the wall, so we can find out the rate of heat flow, So, here A is the area of the wall in meter square, dt is the temperature difference, and dx or L is the thickness of the wall. The ratio dt by dx is called the temperature gradient. This is called the temperature gradient. This term is the temperature gradient. Okay. And K is the thermal conductivity of the wall material. So, this is the Fourier law of heat conduction for a plane wall. So, it states that the rate of heat flow in a plane wall is directly proportional to the temperature gradient. Of course, area of the wall is constant, and the proportionality constant which is introduced is the thermal conductivity of the wall material. So, now let us apply this Fourier law of heat conduction for a cylinder. So, this is a cylinder whose inner radius is R1 and the outer radius is R2. At the inner radius R1, the temperature is T1, and at the outer radius R2, the temperature is T2. The length of the cylinder is L. Okay. So, we are going to derive this one, Q, heat conduction. It is a simple derivation. So, let me explain each and every this one. So, if you apply the Fourier law of heat conduction, which is Q equal to minus Ka dt by dx. So, this is for a cylinder, okay. So, which is has got a radial component. So, instead of minus Ka dt by dx, I will be writing dt by dr. Okay. So, the dx refers to the linear component. So, here this is the radial component. So, instead of dx we have to write dr. So, minus Ka dt by dr. Now, I am going to substitute instead of A the surface area of the cylinder. We know the surface area of the cylinder is 2 pi RH, 2 pi RH. So, since already I mean 2 pi RH and where h is the length of the cylinder. So, here I am taking instead of h I am taking L, I am taking L. So, this is the surface area of the cylinder. So, now substitute this A value here. So, it is a very simple derivation. So, instead of A 2 pi RL, 2 pi RL. So, minus K into, so 2 pi RL. So, instead of A I am substituting this term, into dt by dr, into dt by dr. Now, here we have term R, here we have term dr. So, here we have got R, here we have got dr. So, I am bringing this dr and r term to the left hand side, So, this dr is in the denominator. When it goes to the left side, it will come in the numerator, q into dr, and this r will come in the denominator. So, dr by r, q into dr by r, and the remaining terms will be as it is. So, minus 2 pi kl into dt, okay, minus 2 pi kl into dt. Otherwise, let me derive that one, so that all the students will understand. There are some blank slides, so which I will use it to. This is a cylindrical problem which I have taken. So, okay, so let me, q is equal to minus k into a into dt by dr. This is by Fourier's law, okay, Fourier's law. So, A surface area of the cylinder is 2 pi RL, okay, 2 pi RL. So, therefore, Q is equal to minus K into 2 pi RL into dt by dr, okay. So, let me put the bracket clearly. So, bring this dr term to the left side, q into dr, and this r term also divided by r is equal to minus 2 pi kl, minus 2 pi kl into dt, Now, integrate this equation on both sides, integrate this equation on both sides. So, integral q into dr by r is equal to minus integral 2 pi kl into dt, Now, here the variable is dr, okay, dr with dr by r. So, we have to integrate the one with respect to dr, and similarly right side we have to integrate with respect to dt. So, all these terms, other terms are constant. So, q into dr by r is equal to minus 2 pi kl, 2 pi kl can be taken outside the integral, which is a constant term, integral dt. So, q in the limits are, okay. So, here if you see the diagram, if you look at the diagram, at the radius r1 the temperature is T1, at the radius r2 the temperature is T2, okay. So, the limits will be like at when r equal to r1, T equal to T1, when r equal to r2, that is at the outer radius, the temperature is T2. So, at r equal to r1, that is inner radius, T is equal to T1, and at r equal to r2, the temperature is T2. So, the limits will be
q into integral r1 to r2 dr by r is equal to minus 2 pi kl t1 to t2 dt.
So, this integration is very simple. Left side you will get ln r,
q into ln r
1 by r dr is ln r,
lower limit is r1, upper limit is r2, and right side it will be minus 2 pi kl into
integral of dt is t,
upper limit is t2, lower limit is t1. Upper limit is t2, lower limit is t1. So let me erase this. So now apply the upper limit and the lower limit. Q ln of r2 minus ln of r1, q into ln of r2 minus ln of r1 minus 2 pi kl into,
apply the limit on the right side, t2 minus t1.
So this minus this can be written as, since minus term is outside, this can be written as 2 pi kl into t1 minus t2, q into, and left side can be written as ln a minus ln b, ln of a by b. So ln of r2 by r1. Therefore q is equal to 2 pi kl into t1 minus t2 divided by ln of r2 by r1. So this is the
final equation which we will get when we derive by applying the Fourier law of heat conduction. Q equal to 2 pi kl T1 minus T2 by ln of R2 by R1. So now let me go to back to the derivation. 2 pi kl T1 minus T2 divided by ln of R2 by R1. So that completes. So this is for the heat conduction in a cylinder. Next we will be doing the same thing for a sphere. At radius R1 the temperature is T1 and at radius R2 the temperature is T2. So applying the Fourier law of heat conduction, let me do it quickly. So this is a spherical problem. So let me do by Fourier's law of heat conduction. Q equal to minus Ka dt by dr. So again we should not write dx, for a radial company we write dr, change in radius. Surface area of a sphere is 4 pi r square, for a cylinder it is 2 pi rl, for a sphere it is 4 pi r square. So substitute the value of A.
So Q is equal to minus K into 4 pi r square into dt by dr.
So like the previous derivation, dr term and radius term to be on one side, the other terms on the other side.
So Q into dr divided by r square is equal to minus 4 pi k,
r square I have brought to the left side denominator,
into dt. Integrate on both sides. So Q into integral dr by r square will be equal to minus 4 pi k will be constant, integral dt.
So let us write the limits also. When at radius r1
the temperature is T1, at radius r2 the temperature is T2.
So the limits are same for both the cylindrical component and the spherical component.
Now this can be written as dr by r square can be written as q into integral r1 to r2 r power minus 2 into dr.
So I have taken the numerator term, denominator term to the numerator, like 1 by x square equal to x power minus 2.
minus 4 pi k into integral T1 to T2. Now, integral of r power minus 2 is r power minus 2 plus 1 by minus 2 plus 1. So, q into r power minus 2 plus 1 divided by minus 2 plus 1. Lower limit is r1, upper limit is r2. Right side minus 4 pi k is constant. Integral of dt is t. So, upper limit is t2, lower limit is t1. Now, we can simplify this one. So, q into r power minus 2 plus 1 is r power minus 1 divided by minus 1, r1 to r2 minus 4 pi k, okay, into t into t2 t1. R power minus 1 can be written as 1 by r. So, already we have one negative sign. So, q into minus 1 by r. So, after writing this one, if you apply the limits and take LCM, we will get the final expression minus 4 pi k into T2 T1, T2 T1. Now, let us apply the limits on both sides. Okay. So, q into minus 1 by r2 when we apply the upper limit, upper limit minus lower limit. So, we have already one minus sign. So, minus of minus will become plus equal to minus 4 pi k. Here upper limit is T2 minus lower limit is T1. So, left side we have to take LCM. Okay. So, the LCM is R1 into R2. So, minus R1 plus R2. Right side multiply by minus sign. So, we can write 4 pi k into T1 minus T2, T1 minus T2. So, q into R2 minus R1 divided by R1 into R2 equal to 4 pi k into T1 minus T2. So, therefore, q is equal to 4 pi k T1 minus T2 divided by R2 minus R1 divided by R1 into R2. So, this can be written as the denominator R1 R2 can be taken to the numerator. So, we get the final equation as q is equal to 4 pi k inner radius into outer radius into delta t, that is T1 minus T2 divided by outer radius minus inner radius. So, this is the heat conduction equation in case of a sphere. So, if you see the one which we have derived, 4 pi k into inner radius into outer radius into T1 minus T2, heat flow is from T1 to T2, T1 to T2 divided by the difference radius R2 and minus R1. So, this is the heat conduction equation for a sphere. Okay. The next one is the thermal conductivity. So, this is a very important property. So, it is the ability of the material to conduct heat. So, it is expressed by the letter small k. Generally, we use capital K for Kelvin, small k refers to thermal conductivity. Its unit is watt per meter degree centigrade or watt per meter Kelvin, okay, because it is the change in temperature, difference in temperature. Okay. So, watt per meter centigrade or watt per meter degree centigrade or watt per meter Kelvin. So, this table shows the comparison of the thermal conductivity value, K value and Cp value for 3 different substances. Okay. So, one is solid, one is liquid, one is gas. So, copper has got a K thermal conductivity of 401, but its specific heat capacity is very, very less, 0.39, that is in kilojoule per kg Kelvin, the units I have given. Water has got good Cp value, the K value is 0.607, and air of course compared to water, the Cp value is 1/4 and the thermal conductivity is also okay. So, just to have an idea,
compared the thermal conductivity of the different materials, one solid, one liquid, solid, liquid and gas. Now, let us solve some numericals with this background. Okay, so I will be solving 4 numerical questions, 2 questions related to plane wall, 1 numerical related to cylinder and 1 numerical question related to sphere. So, the first one is 1.2 kg of liquid water initially at 15 degrees centigrade is to be heated to 95 degrees centigrade in a teapot equipped with a electric heating element. So, the initial temperature is given, final temperature is given. The weight of the teapot is given and it has an average specific heat of, the mass of the teapot is given kg, that is 0.5 kg, and it has an average specific heat of 0.7 kilojoule per kg. Neglecting any heat loss from the teapot, determine how long it will take for the water to be heated. How much time it will take to heat the water from 15 degrees centigrade to 95 degrees centigrade. Okay, so let us, this is mass only, so no need, we should not write m dot, it is m. Okay. So, the quantity of water is given as 1.5. Now, let us write this one, mass of water okay, mass of the teapot is 0.5 kg. So, Tp refers to mass of teapot 0.5 kg. Cp of teapot is 0.7 kilojoule per kg Kelvin. So, specific heat capacity 0.7 kilojoule per kg. Okay. And the Cp of water, if it is not given, even if it is not given, we know the Cp of water and air. So, 4.18 kilojoule per kg Kelvin. Initial temperature is T1, final temperature is T2. So, the water is heated from T1 is equal to, let us write the temperatures here, 15 degrees centigrade. Okay. It is 15 degrees centigrade and the T2 is 95 degree centigrade. So, there is a delta T of 80 degree centigrade. Okay. So, first we have to find out the one more data is given, the heating element, electric heater, that one how much the wattage 1200 watts. So, that we will use Q value, okay, small q 1200 watts. Okay, so, it is given. So, now we have to find out the capital Q, that is the rate of this one, heat flow, okay, how much heat is required, mCp delta T, mCp delta T. So, here Q is equal to m into mass of water, Cp of water into delta T of water plus mass of the teapot, Cp of teapot into delta T, Okay, of course, delta T is this one. Say it is the same because the water is contained in the vessel, in the teapot. Okay, so, now we have to substitute the values. Mass of water is 1.5 into Cp is 4.18 into delta T 95 minus 15. So, this is the first part. Okay. So, let us take delta T as it is, okay, plus mass of teapot is 0.5 into 4.18, Cp of teapot is 0.7. So, this is for teapot, this is for teapot, this is for water. So, the values
Pertaining to teapot I have underlined. Okay, so mass of teapot is 0.5. So 0.5 into Cp of teapot is 0.7 into 95 minus 15. So if you calculate, okay, so you will get 429 kilojoules of heat. 429 kilojoules of heat. 429.3 kilojoule. M is in kg. This is kilojoule per kg. So kg and kg will get cancelled, and delta T temperature difference. So you can substitute in degree centigrade or Kelvin, doesn't make any difference. So the temperature the unit will get cancelled. So we will be left out with kilojoules, 429.3 kilojoules. Now this Q is equal to 1200 watts. Watts is nothing but joules per second. Joules per second. So here I am having kilojoules. Okay. Okay. Now time is equal to, okay. So let us convert this also into kilojoules per second. So this is equal to 1.2 kilowatts or kilojoules per second. Kilojoules per second. So divide the Q value, okay, divided by small q. So this is in 429.3 kilojoule, and this is 1.2 kilowatts, or which is nothing but kilojoules per second. Kilojoules per second. So the kilojoule term will get cancelled. Okay, we will get the answer in time. Okay. Close to 6 minutes, 358 seconds. So this is, you will get the, so because this is in joules per second. So the answer which we are getting, it is in seconds. Okay, divide by 60. So T is equal to 6 minutes. So it will take 6 minutes for the based on the data which is given in the numerical question, for the water to be heated from 15 degree centigrade to a temperature of 95 degree temperature, 95 degree centigrade. Okay. Now let us move to the second question. Consider one dimensional steady flow heat flow in a plate of 20 mm thickness with a uniform heat generation of 80 megawatt per meter cube. 80 megawatt, that is 80 into 10 power 6 watts per meter cube. So for one cubic volume, so this much is the internal heat generation. The left and right faces are kept at constant temperature at 160 and 120 degree centigrade respectively. The plate has a constant thermogeneity of 200 watt per meter Kelvin. So K value is given. Determine the location of the maximum temperature within the plate. So there are two things which we need to find: at which point, at which location, what is the value of x at which the maximum temperature occurs, and what is the value of that maximum temperature. So that is the second one. So this is the schematic, based on the information given in the question. So I have just converted that into a schematic. So it's a plate is given. Okay, so it is given in a plate. So it is like a plain wall. It is like a plain wall. So as mentioned before, the thickness is given as is taken as dx, which is equal to L. So here the temperature is 160. Here it is 120. So we need to find at which point on the x-axis, at which location on the x-axis the maximum temperature is attained, and what is this maximum temperature. Okay, so let us write this value, small q. Okay, so this is actually q dot. We will take q dot. Okay, small q is capital Q by A, that is heat transferred per unit area. Okay, so let us take this as q dot, and this is 10 power 6. Okay, so now q dot is given. So let us take that, because capital Q we find it in watts, small q is watts per meter square. Okay, small q is equal to capital Q by A, capital Q by A we will get, and we will use this q dot for this per cubic volume. Okay.
However, the notations used varies from one book to another book. Most of the books will use a similar one, sometimes they will use, but we need to define it very clearly. So, the temperature at this is here x is equal to 0, here x is equal to L. At the left extreme face, the thickness of the wall is 0, and on the right extreme it is L. Okay. So, that is given as 20 mm, this is the thickness, it is given in the problem. Dx is equal to L equal to 20 mm, and K value is given. Okay. So, if we apply the one dimensional steady flow equation for a plane wall, okay, or for a plate in which internal heat generation is there. So, this is the standard equation, d square T by dt square dx square plus Q by K is equal to 0. So, this is the internal heat generation Q dot. Okay. So, let me write this equation, d square T by dx square plus Q dot by K. Normally, the dot is used for whenever there is an internal heat generation term. Okay. So, Q dot by K is equal to 0. Okay. So, let us take this as equation number 1. Let me again emphasize the data given, temperatures are given, thickness of the wall is thickness of the plate, which is this configuration is similar to plane wall. So, the thickness is given as 20 millimeter, okay, and K value is given 200 watts per meter Kelvin. The temperature when at extreme left, on the left extreme left face it is 160, and on the extreme right it is 120. Okay. So, now to find out the maximum temperature, so we need to before this is d square T by dx square plus Q dot by K, that is the standard equation. So, we have to integrate this equation twice. So, we will get two constant C1 and C2, or constant can be A and B also. So, first one is integrate this equation. Okay. So, this will be equation number 1, integrate equation number 1. So, this will be dt by dx plus Q dot into x by K equal to constant C1. So, this will be equation number 2. Okay. So, that is what I have got here, dt by dx plus Q dot by K into x into C1. Again integrate this equation, the equation number 2. Okay. Now, integrate, first I am integrating equation 1. So, d square T by dx square reduced to dt by dx. So, integrate equation 2. So, we will get T as a function of x plus Q dot into x square by 2, x is x square by 2, already I have got K. So, we will get 2K equal to C1 into x, and one more constant will come C2. So, this is equation number 3, equation number 3. T plus Q is so equation number 3. Now, substitute the value of Q and K. Q is given as 80 megawatt, okay. Q is given as 80 megawatt per meter cube. So, that is nothing but 80 into 10 power 6 watts per meter cube. Okay. Q dot is given. Okay. Q dot is heat quantity per unit volume, it is not area, it is unit volume. So, substitute value of Q dot and K in equation 3. So, okay. So, due to time constraining, I am just writing this one directly. So, we are getting this equation number 4, T plus 200 into 10 power 3, okay, and simplifying T plus 200 into 10 power 3 into x square equal to C1x plus C2. So, this is after simplification, okay, into x square equal to C1x plus C2. So, this will be equation number 4. We need to find out the value, the constant value C1 and C2, then only we can find out the value of x, and we can find the maximum temperature T max.
Okay. So, this is equation number 4. Now, the boundary conditions are very clear. If you look at the diagram, at the point thickness is equal to 0, temperature is 160, when thickness is equal to L, okay, that is when thickness is equal, L is 20 mm, okay, that is 0.02 meter, the temperature is 120, the temperature is 120. So, the boundary conditions are at x is equal to 0, okay, temperature is equal to 160 degree centigrade. At x is equal to L, the thickness of the plate is given, okay, that is 20 mm, 0.02 meter, the temperature is 120. So, these two to be substituted, okay, in the, okay, when you substitute x is equal to 0, when x is equal to 0, temperature is equal to 160. Therefore, equation, okay, therefore, equation 4 becomes, so if you substitute x is equal to 0, here x square term is 0, so this term will get cancelled. So, it will be t plus 0, x is equal to 0 equal to C2, and value of t is, we are substituting 160, okay. So, this will be 160 plus 0, okay. So, the equation 4 will become, equation 4 will reduce to 160 plus 0. So, that means we get the constant value 160, okay. Similarly, when you apply x is equal to 0.02, when x is equal to 0.02, temperature is equal to 120, okay. So, substitute the value of C1 and C2, and when substitute now substitute the value of C2 also, okay. So, what we have to do is we have to substitute the value of C2 160, C2, okay, x is equal to 0.02 and t equal to 120. So, we will get the value of C1, the constant one can be found, okay. So, constant one, the value is 2000. So, equation 4 becomes 2000. Now, we know C1 and C2. Now, we know C1 and C2. Substitute the value of, again take equation number 4 and substitute C1 and C2. Value of C1 and C2 in equation 4, okay. So, let us quickly solve this one. So, we get this equation t equal to 2000 x plus 160 minus 200 into 10 power 3 into x square, okay. Now, for maxima, we know the basic this one, differentiate with respect to x, okay, differentiate equation 7 with respect to x and equate to 0, okay. So, t equal to 2000, let me write this one, t equal to 2000 x plus 160 minus 200 into 10 power 3 into x square, 200 into 10 power 3 into x square. So, differentiate this equation dt with respect to x and equate to 0. So, you get the maximum this one. So, once you do this one, we get x is equal to 0.005 meter, okay, that is 5 millimeter, x is equal to 0.005 meter. So, the value of x is equal to 0.005 meter, okay, or 5 millimeter, and T max is 165 degree centigrade, 165 degree centigrade. So, here if you see the diagram, T max is above this point. So, obviously, it should be greater than 160. Okay. So, that completes the problem. Let us quickly go to the third problem. Third and the fourth problem are very simpler. A steam pipe of length 20 meter. Okay. So, it is like a cylinder, cylindrical component. Thermal conductivity K value is given, inner and outer radius are given, R1, R2, T1, T2 is given. Okay. So, it is very easy. Okay. If you see this one, L is given, we know the value of L, L value is given, T1 is given, T2 is given, R1 is given, R2 is given. So, you have to find out Q. Okay. 2 pi KL, use this formula 2 pi KL. This is for this is the formula which we derived by applying Fourier law of heat conduction divided by ln of R2 by R1. So, all the data are given and you can find out the value of Q. So, it comes to 785.8 kilowatt. Next one is a spherical component. So, I will be applying the Fourier law of heat conduction which we derived for a sphere. K value is given. Okay. So, here I will write this one numerical question. K value is given. We know R1, R2, T1, T2. So, you can find out. Okay. So, use this equation 4 pi 4 pi R1 R2 into K into T1 minus T2 the whole divided by R2 minus R1. Okay. So, to let me summarize, in this lecture we have discussed about the modes of heat transfer, that is conduction, convection and radiation, the meaning of the property thermal conductivity, it is the ability of the material to conduct heat, and we have derived the Fourier law of heat conduction for a cylinder and a sphere. According to Fourier law of heat conduction, Q is directly proportional to the temperature gradient, and to remove the proportionality term, a constant is used. The constant that was used is the thermal conductivity of the material, and we have applied the Fourier law of heat conduction for a plane wall. We have solved numerical for a plane wall, which is in the form of a plate. Two numericals were solved pertaining to plane wall, one with regard to cylinder and one with regard to the sphere. So, with this let me conclude the lecture number 25. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.